have spent millions of dollars to explore the surface of the moon. Minerals. What's the depth and extent of ore bodies? How much water is there? What's the topography? Where are the best transportation routes? How much will they cost per mile? Where are the best landing sites? We have spent millions of dollars to explore the surface of the moon. But what do we really know about the Earth and its resources? Where are those resources? How great are they? We are in a race against time. 1 billion people are hungry. All their time is used to find food. They are losing the race. The world is losing their potential contribution. How can productivity be increased? What resources can be developed? How fast? And at what cost? How should the benefits be distributed? We need information. Data on resources has been piling up for years, even in the newest countries. The problem is how to store it, measure it, and analyze it. Just to look at it, using conventional methods, would take years and years. To make decisions, we need facts. But we have facts. We have all seen soil maps and census figures. So what's the problem? The problem is not making the surveys. It is trying to read and summarize the results of the surveys. The amount of work involved in handling this data is enormous. Even the simplest operations take hundreds of people. Raw data and statistics have to be cataloged, stored, summarized before the data can be used to make decisions. The process is painfully slow. It's bad enough when you're handling census data. It's even worse when you have to handle maps. And so much of our land information comes only in maps. Suppose an administrator wants to find out how much good farming land in his province is still undeveloped, and where. He has to compare the maps showing good farming areas with the ones showing present land use. But they are not at the same scale. First, one map must be remade as a transparent overlay at the exact scale of the other map. Checked, retouched, positioned. To measure the area where both factors overlap, he will probably use a dot grid, a method that hasn't changed since the days of ancient Egypt. What if he wants to consider other factors, such as the incomes of the people, crop yields in a certain soil, forestry, wildlife, recreation, climate, census data? To compare two factors over 100 square miles will take one man a whole working day. To compare only 6 basic factors for all of Canada would take 556 people 8 hours a day for 3 years. It would cost $8 million. But we don't have the staff, we don't have the time. More resource data comes in every year, every month, every day. Crop and forest assessment, soil surveys, forestry surveys, timber pest counts, wildlife surveys, sampling, analysis, and many others. Where have surveys been made? Where do new surveys need to be made? To make our decisions wisely, we will need every bit of this information, and even more.
Human beings alone can't handle this vast amount of information. But if we harness the computer and use it to extend our abilities, then we can. At the moment, the government is rather like a farmer who's just inherited his farm. He doesn't really know how big the farm is. He perhaps doesn't know much about the soil. He hasn't got too much idea about the climate, and he's not really sure whether there's usable water. And yet, he has to make decisions that will let him plant the right seed and grow enough food to support his family. And if you think that would be a problem on an ordinary-sized farm, think what it would be like with 1 million square miles. The Canada Land Inventory is trying to tackle this problem in 2 ways. Firstly, it's trying to gather together the basic information that we need to know about the country. Secondly, it's trying to find out some way of handling this information. We like to think that we've got a system that can accept the information, can store it, can analyze it, and present the results in a usable form. A system that can do this not in years, but in hours.
The computer can be an instant library, a bank of information. Information that is stored as numbers, on tape in this case. It can store statistics, and these statistics can be filed for immediate access at any time. However, so much of the information about land resources comes only in maps. How can we store them as numbers? But we've used a number system for centuries. Latitude and longitude. Any point on Earth can be identified by numbers, even boundaries, areas, or lines. And for any point on the Earth's surface, we can add other data, described by numbers. The location of road and railway bridges, landing fields, sources of power, industrial sites, and the capability of the land itself, land for forestry, soils for farming, pasture land, wildlife areas, land with recreation possibilities. All these factors can be stored and compared with other information about the land and the people who live on it. Map information is located, described, and fed, one factor at a time, into a drum scanner, which reads off the value, at this scale, for points every 100 feet across the country. These signals are stored on tape. The map has been turned into numbers. Just as the human eye looked down through the overlays to compare 2 factors, so the computer can compare 2 sets of numbers. 2 factors, or as many as necessary. Soils, climate, topography, wildlife, farm and forest capability, and even more important, it can compare all of these with statistics on human resources, census figures by subdivision, average income, family size, age, and information on human needs, employment, costs of development. The computer can look at all these figures, compares them, and puts out the analysis we have asked for, in statistics or in map form, on any scale desired. This is the way we can store information for future use. Compare it, measure it, or print out the analysis in map form. This is the basic concept of the Geographic Information System. Here it is in actuality. The drum scanner is capable of converting into numbers up to 6,000 maps per year. The lines on the map are recorded with an accuracy of 1/10,000th of an inch and stored by an optical scanning device on magnetic tape. The scale of the map is not fixed. It can be reproduced on any scale at any time. $5.99, $600. Each of the map areas is given a number. And on a digitizer table, a coordinate. A key coordinate is recorded within each area. The coordinates are stored on punch cards. The information has been located geographically, and it is described on another set of punch cards. By collating the two card sets, the information and the key coordinates are merged together, so that each area now has its number and name stored inside the computer. This information can be changed or updated at any time. First, it is checked for errors by the computer. If we could visualize what the computer does electronically, we would see that it discovers omissions and misinformation introduced by human error. These errors are printed out. The necessary corrections are made either by changing the information on punch cards or by tracing the correct lines and loops with the digitizer. The corrected map information is fed onto the tapes. This, then, is the storage system of the Canada Land Inventory. For the first time, we can use all of the information we've gathered over the years. Special maps can be made on request. Suppose an administrator wants to know how many viable farms his region can support. He fills out a request using plain language. This is a normal request. The computer could handle many other factors as well. Farmland could be measured in relation to good roads, or freight rates, or profits over cost per acre. The request is translated into code, and the code into punch cards. A similar request has been made before. The computer refers us to an existing file of statistics and maps. As our administrator looks at the file, he formulates another, more complex question. These are the viable farms. But what about people who live in other areas? Are there possibilities for recreation, wildlife, or forestry? Where should the government invest in development? What is the best land use in each area? What are the human resources, education, income? The computer indicates the tapes on which all this information is stored. Now it will compare and analyze all the factors at a speed that human hands could never match. The administrator no longer has to make decisions by guesswork. He has access to all the available information concerning land. He can get it in map form, on any scale, instantly. The computer can replot these maps at any scale with the accuracy of oceanographic charts. But even when a map has been prepared, the administrator can study it and alter his request to get the combination of information best suited to his needs. The information he has received suggests where the problem lies. One of the 3 counties has good land, but its farmers have very low incomes. Why? He needs more detail as soon as possible. He starts to ask what information we have about the area.
I'd like to take another look at those 3 counties in Ontario, Omar, Otter, and Birch County.
Okay.
Can you give me the enumeration areas for Birch County?
Yes.
That's too small. Can you blow it up a bit?
Yes.
I'd like, we're going to need some information. Can you set up the enumeration area data block?
Okay.
And how about the number of farms?
Okay.
What's this W36 here?
Well, there was only one farm in 37, so it was included in 36 for confidentiality.
Could you give me average gross sales on the
I think that's on here.
column 2? It's not very good, is it?
Oh, pretty low.
Low-income farms on good land? Are there too many farms? Are they too small to be viable?
What about the capability? How many farms could the area support?
What input assumption?
Oh, assumption P.
Okay.
That's less than half of the present number.
Yes.
Let's have a look at the education, average level of education, and keep the figures in column 1. Would you?
Okay.
He calls in census data. Now he knows the size of the problem.
Let's have
Can the government develop other resources in the area?
Could give me the forest capability?
For all three counties?
Yes, for all three counties.
Okay.
The recreation? Put them together.
Okay.
Yes, that looks quite promising.
The problem is not solved yet. Much work needs to be done. But for the first time, much of the information he needs is accessible and useful. The data is in the hands of the decision makers.